Hello, eighth grade. It's Mrs. Rienzi, and I have another class for you. I have to admit that I'm feeling rather frustrated because I tried a new screen recording platform today that doesn't have the 15-minute limit. And I talked to you for about 35 to 40 minutes and it didn't upload. And then I did it again because I thought I had figured out the problem. And I did the whole 35-minute class again and it didn't upload. So I am back to the 15-minute platform. So what I'm going to do is I'm not going to show the videos within this. In the other platform, I could embed the videos in, and that's why I liked it better, so you didn't have to go back and forth. But unfortunately, you're going to have to pause and go back to get the videos. And I'm sorry about that. Hopefully I can figure out this new platform by the next time we do this. You should have the handout with today's questions. Have that out and ready to take notes. All right, let's get going. So we've talked about pressure generally, and we talked about air pressure specifically at the end of last week. Today we are going to talk about water pressure. Water pressure is the weight of water pushing down on an object, and water pressure increases as depth increases. So the deeper you dive underwater, the greater the pressure becomes. Why is that? The deeper you go, the more water there is above you. So you have more weight, the weight of the water to support. In addition to all the water that's on top of you, and obviously more water the lower you go, you also have air in the atmosphere that's pushing down on the water. So the total pressure at a given point beneath the water is the weight of the water plus the weight of the air above it. In the deepest parts of the ocean, the pressure is actually more than 1,000 times the air pressure you experience every day. This is why scuba divers have to be really careful not to rise to the surface too quickly. When the pressure decreases too rapidly, humans can experience something called decompression sickness. It's also sometimes called the bends. And this is when the pressure decreases rapidly and it causes nitrogen bubbles to form in the tissues of the body. This causes pain in the muscles and joints, cramps, numbness, nausea, and paralysis. So that's why they have to be very careful. And as they ascend, they have to do it slowly enough that they don't get decompression sickness. So now we know that you have the weight of the water pushing down on an object along with the weight of the air pushing down. So how do things ever float if you have all that weight pressing down on an object that's in the water? All right, so floating is when an object does not sink in the water but remains suspended in the fluid. A common misconception is that heavy things sink and light things float. But think about a large ship. What causes a large ship to float, whereas like a steel bolt, a little tiny bolt, will sink down to the ground, to the bottom? Buoyancy. Buoyancy is the tendency of an object to rise or float in fluids. You can also think of it as the ability of a fluid to support an object floating in or on the fluid. All right. And now we're going to talk specifically about the buoyant force and how buoyancy works. If you've ever picked somebody up when you're in the pool, you'll have noticed that they seem much lighter in the water than out of the water. You probably, had fun picking up your dad or your mom in the water when you were a little kid. And the reason you were able to do that was because of something called buoyant force. It's also why if you've ever tried to push a swim float completely under the water, it pops back up at you all the time. Or if you've dropped your swim goggles in the deepest part of the pool and tried to swim down to get them, you feel the water trying to push you back up to the surface as you're swimming downward. The name of this upward force exerted on objects submerged in fluids is called the buoyant force. So why do fluids exert an upward buoyant force on objects that are submerged? It has to do with differences in pressure between the bottom of the submerged object and the top of the submerged object. So we know that fluid exerts pressure on all of the surfaces of a submerged object, on the top, bottom, sides. And since pressure in a fluid increases the deeper down you go, right, because there's more water on top of you, the upward pressure on the bottom of the object, because it's deeper in the water, is greater than the downward pressure on the top. So then you have an unbalanced force. And we learned about unbalanced forces in the last unit. When you have an unbalanced force, you have a net force, in this case, pushing up on the object because the greater force is on the bottom. And this is the buoyant force. So here you can see someone dropped a can of beans in the water, and you can see that there's more force pushing up on the bottom of the can because the bottom is deeper in the water than the top of the can. So that creates a buoyant force, right? Pushing up on the water. So why does anything ever sink, right? If you always have a greater pressure pushing on the bottom, why does anything ever sink to the ground? The upward or the buoyant force is working in opposition to another force, and that is the downward force of gravity. And as a result, depending on which force is greater, and we're going to learn a little bit more in a second, the object will either float, sink, or remain suspended in the water. All right, so an object can be negatively buoyant. This means that the weight of the object is greater than the weight of the water it displaces. We're going to talk a lot more about displacement of water in a minute, but just for right now, know that an object sinks if its weight is greater than the buoyant force. An object can be positively buoyant. This means that the weight of the object is less than the weight of the water it displaces, and the object will float. Or an object can be neutrally buoyant, and this is when the weight of the object is exactly equal to the weight of the water it displaces. There is no net force acting on the object, so the object remains suspended mid-water and will neither float nor sink. Now, some of you, if you've been paying good attention, will be thinking to yourselves, I thought you said it was a common misconception that heavier things sink and lighter things float. Notice, though, in each one of these descriptions, they're not saying that a heavy object or the weight of the object is what makes a difference. It's the weight of the object has to be greater than the weight of the water it displaces, right? So a heavy object that displaces quite a bit of water will float. We'll learn a lot more about that in a couple of slides when we learn about Archimedes' principle. But know that it's much more than just the weight. It's the weight in comparison to the weight of the water it displaces. All right, and here's a picture where you can see this in action. So in the middle one, that's showing it almost equal, right? You have 9 pounds pushing down and 10 pounds pushing up. So that's why it's not suspended right in the middle of the water and it's bobbing up above the water line. Had it been 10 pounds and 10 pounds, then you would have seen it suspended under the water line. Okay. All objects take up space. We know that. And so what happens when you place an object in water? That object now takes up space where the water used to be. So where did that water go? In physics, we say that the water gets displaced. If you were to fill a cup with water all the way up to the brim, what would happen if you added ice? The water would spill out, right? Because now the ice is taking up space in the cup, pushing or displacing the water out. Okay, so now we understand what displacing means. It just means that it takes up space in the water, and that water that used to be in that space has to go someplace. You may have heard of a Greek mathematician and philosopher named Archimedes. He's famous for his eureka moment in the bathtub. He actually discovered a connection between the weight of a fluid displaced by an object and the buoyant force acting on it. So there's this legend that Archimedes first discovered buoyancy while puzzling over a problem posed to him by the king of Syracuse. According to the story, the king thought that his gold crown was not actually made of pure gold, but rather a mixture of gold and silver. He thought he had been duped. So, allegedly, while taking a bath, Archimedes noticed that the more he sank into the tub, the more water flowed out of it. And he realized this was the answer to the king's puzzle, and he rushed home, supposedly naked, while crying, Eureka, which is Greek for I found it. Archimedes then made 2 objects, one gold and one silver, that were the same weight as the crown, and he dropped each one into a vessel filled to the brim with water. He observed that the silver mass caused more water to flow out of the vessel than the gold one. Next, he observed that the king's supposedly gold crown caused more water to flow out of the vessel than the pure gold object that he had created. So even though the 2 crowns were of the same weight. So Archimedes was able to prove that the king had indeed been duped. So according to this legend, Archimedes demonstrated that the king's crown indeed contained silver. And this does illustrate an important principle of buoyancy, but it's most likely not a true story. One, Archimedes recorded his observations and his science experiments, and this is not recorded anywhere. And also, if a tiny amount of silver were indeed swapped for the gold, the amount of water displaced would probably be too small to reliably measure. So this story is most likely not true, but it has become a very popular legend. I thought this was funny. In Israel, they have this statue with water in it of Archimedes in his tub. I want you to pause the video now, and you're going to watch the true story of Archimedes, how Archimedes discovered the relationship between the weight of the fluid displaced and the buoyant force. So go ahead and watch it. While it doesn't involve him running naked through the streets, it's still a really interesting story. All right, now you're back. Archimedes' principle. The buoyant force acting on a submerged object is equal to the weight of the fluid the object displaces. That is what Archimedes' principle states. Another way to say this is that every object is buoyed upwards by a force equal to the weight of the fluid the object displaces. This means that if you want to know the buoyant force on an object, all you have to do is figure out the weight of the fluid displaced by the object. So if this is still confusing, think about what would happen if you put a little baby pool in your backyard and you filled it to the very top full of water. And imagine you had a way to collect the water as it spills out when you get in. So you're going to get in, the water that you displace is going to spill out, but you have a way to collect the water. Maybe you have like a little thing that looks like a moat that's collecting the water. If you could measure the amount of water spilling out of that baby pool, and let's say you measured and it said that your body displaced 50 liters of water, then you would know, according to Archimedes' principle, that the buoyant force exerted on you would be equal to the weight of 50 liters of water. And this is about 500 newtons. Okay, so that's a really important principle that Archimedes discovered. And if you're still having a difficult time with it, you can pause this and watch this video. This is a very short video, but it does a great job of explaining Archimedes' principle. I would pause it and watch it unless you feel completely confident that you understand how it works. All right, so Archimedes' principle helps explain why a ship floats. Since the buoyant force equals the weight of the displaced fluid, the buoyant force will increase if more fluid is displaced. In other words, a large object displaces more fluid than a small object. Therefore, a greater buoyant force acts on the larger object, even if the large object has the same weight as the small object. So take a look at this block of steel, and then you have this steel ship. And the block of steel sinks all the way down to the bottom, whereas the steel ship is floating on the surface. The reason is that the shape of the ship's hull, this bottom purpley part down here, causes the ship to displace a greater volume of water than a solid piece of steel with the same mass. The ship displaces a volume of water equal in weight to the submerged portion of the ship. Since a ship displaces more water than a block of steel, a greater buoyant force acts on the ship. So a ship will float as long as the buoyant force acting on it is equal to its weight. So it's really important when a shipbuilder is designing a ship that they design the shape of it to displace enough fluid to hold the ship up so that it doesn't sink, right? To have it float at the surface rather than sink. All right, so we are going to get into density. Density is the amount of substance that occupies a particular space. Another way to think about it is density is the crowdedness of particles. Remember how we said a common misperception that a lot of people have is that whether an object sinks or floats depends on its weight? But the truth is it actually depends on its density. If an object is less dense in the fluid, it will float. If it is denser, it will sink. So how do you calculate density? Density equals mass divided by volume. Okay, so you have 1 cubic centimeter of lead has a mass of 11.3 grams. So we're keeping it simple with a volume of just 1 cubic centimeter. The mass is 11.3 grams. So if you do 11.3 grams divided by 1 cubic centimeter, you see that the density of lead is 11.3 grams per cubic centimeter. In contrast, 1 cubic centimeter of cork has a mass of only about 0.25 grams. So the density of cork is about 0.25 grams per cubic centimeter. Then we know the density of water, or I'm telling you now, you didn't need to know it before, is 1 gram per cubic centimeter. So water is less dense than lead, so that's why the lead sinks, but more dense than cork, which is why cork floats. All right, so there's the cork floating. All right, so what you are going to do next is you are going to do some density calculation problems. I couldn't finish up the whole unit on density right now because we're running out of time, but we'll get back into it on Wednesday. There's only a little bit left, and then we'll finish the water pressure unit. But for right now, you're going to get onto IXL. There's now a science section. I'm sure you guys are thrilled. I know how much most of you love IXL, and I will say I know IXL can be frustrating because I know that it can give you trouble if you miss right when you're at the end of completing. Do not spend more than 20 minutes on the skill on D1. It should not take you 20 minutes, but if for some reason it's taking you more than 20 minutes, just stop. You email me and explain what happened, either that you made a typo and it sent you back to the beginning, or you're just, you're finding this challenging and you need a little extra help. So do not do more than 20 minutes on the IXL. If for some reason you forgot your password or your username, email me. I have that information. All right, I'm really running out of time. Have a great day. I hope some of you sign up for the elective. Talk to you soon. Bye-bye.